Hi, this is Tom. Welcome to my channel. I studied real analysis some 40 years ago, about 1983, and recently decided to revisit the subject, and I'd like to share some things I've been looking at. I've been studying with AI, which is an excellent tutor, and this web app that I'm going to be using to illustrate the proof was made with AI, and I intend to do two videos. So one will be a math video, which is this one, and then another one will be for those that are interested in AI web development. I'll show how this app was built. So the theorem that we're going to look at is the monotone convergence theorem, monotone convergence theorem. And the precondition is that you have a sequence which is bounded. And we're going to consider the case where it's bounded from above. And so we're going to show that the sequence will converge. So we're going to start off just kind of looking at the idea from an intuitive standpoint. And then we will look at the proof itself. And I'll mention that there's several ways that this theorem can be proved. And the one that we're looking at here will be the one that involves using sequences. So to start off with, we are going to assume that we have a sequence, AN, which is monotone increasing and bounded from above. So since it's monotone increasing, each subsequent member of the sequence will be greater than or equal to the one that precedes it. So you can think of this as x1, x2, x3, and so forth. Now, if we had a divergent sequence, we could have one that was unbounded that went up to infinity, but we're looking at one that's bounded. So there will be some bound above our sequence that's greater than or equal to all the values of our sequence. And from an intuitive standpoint, since we can think of the bound as a type of wall, and since the sequence is monotone increasing, it either has to level out at some point, or it's going to be increasing until it runs into the wall and like asymptotically grows closer, but there's going to be some point where it can't go over because it's bounded. So now let's look at the proof. So we're going to start off with a set of terms, which is we have the terms of our sequence, AN, where N is the indices of N are positive integers from 1 to infinity. And we're looking at the case where our sequence is bounded from above. Now, since we have a bounded sequence that's not empty by the completeness axiom, there is a supremum, also known as a least upper bound. Now, since we have a supremum or least upper bound, we can't have any upper bound which is less than the supremum, the least upper bound. So for any epsilon that we look at that's lower or smaller than our least upper bound or supremum, there has to be members of the sequence that are within that gap. So that's what this is illustrating. And the reason is that if there weren't, then we would have an upper bound that was a lower value than the least upper bound, which is impossible. So at some point, there is a big N such that any subsequent value of the sequence, has an index greater than N, because this is monotone increasing, has to be greater than x sub n. And so here we see that the sequence at some point gets trapped in between the supremum and our x sub big N value. And the key point that we want to get to is what's being shown here. So as we get above n, big N, then any subsequent value of the sequence lies between our limit point L and L minus epsilon. So that's what this is illustrating here. And now the definition of convergence is that for n sufficiently large, which we're calling big N here, the distance between the limit point and x sub big N can be made arbitrarily small. So that's what we're illustrating here, is that we can choose any positive epsilon and we can get the sequence to be within this region that's sufficiently small. So for the definition of convergence is for any n sufficiently large, any x sub n greater, where the index is greater than that n, will be within epsilon of the limit point. And that's what, here is the formal proof. If you want to go through that, it's written out. And again, I invite you to go to the URL and you can take a look at that, and then you can see here that this is the final point here, is that we have the sequence values above big N are trapped between L and L minus epsilon. And then if you just do the arithmetic, you're going to get that the limit point, the distance between the limit point and our sequence values above N are less than epsilon, which is the definition of convergence. So that proves the theorem. Well, thanks for watching. And again, two things to mention. I'll include the URL in the description of the video. And then if you're interested, take a look at, in the web part of it, the web development part, you can take a look at the video that will talk about that, which I'll also include in the description of the video. Thanks for watching, and until next time.